Hello everyone, my name is Timothy Doe. I'm a first year MS-ECE student here at UCLA, and today I'll be doing my paper presentation on RIDL, which is Rogue In-Flight Data Load. And let us begin. Move this here. Yep, now let's begin. So here's an agenda of what we're covering over today. First of all, I'd like to thank the authors, Schaick et al., for providing this paper for us to read. And yeah, so let us begin. So as an introduction, we know that there are many types of transient memory disclosure attacks. However, these memory disclosure attacks have really strict addressing restrictions, those of which is called spectre, meltdown, and foreshadow. Now the first one is called spectre, and what it does is basically it manipulates a branch predictor state for misprediction. How it works is that it requires victims to be in a confused deputy attack, which basically means that the attacker has to trick the user into executing these sort of speculative gadgets in order to leak data. And this data leaks from a covert cache side channel. Now, there's like sort of caveat to this is that this attack only can leak from virtual addresses, and you can mitigate this attack by halting speculations. So the second type of common memory disclosure attack is called meltdown, and basically it accesses privileged addresses from invalid page faults. How it works is that basically the attacker keeps on trying to access this privileged address, and over time, as you keep accessing it, eventually the CPU will reach an error. And before handling that error, the CPU will inevitably expose that data during the out-of-order execution stage, and this can be exploited by the attacker to leak the data. Now, these addresses must appear in some sort of like loaded, like sort of translational address data structure in order for the data to be successfully leaked. And this can be mitigated by something called KPTI, which is a kernel page table isolation, which basically isolates the address spaces of the operating system and the user. Now, RIDL actually bypasses most of these attacks because it does not require that many addressing restrictions, and I'll play the video here. So basically, this is like a demo where it basically leaks the root entry from the etc shadow kernel in Linux. And yeah, after they run their simulations, the amount of bytes it took to leak, they were able to successfully leak the content of etc shadow, the root entry at least. Now, a bit of background about this paper is that the way the architecture they used to sort of find this attack is they use the Intel Skylake architecture, which is a common CPU a few years back. This architecture has a front end, an out-of-order engine, and a memory pipeline. Now, Skylake has 3 levels of cache. The first one being optimized for instructions, micro-ops. Level 2 being more sort of like for buffers, and then level 3 is shared between all the cores. Now, the second component is called the out-of-order engine, which basically this out-of-order execution consists of an order register renaming, out-of-order scheduling, and an order retirement in order to perform instructions out of order. And just as a quick note, Skylake also employs a branch order buffer in order to further assist with its branch prediction unit for speculative executions, and this architecture does it really aggressively. Now, for RIDL, the sources that the authors considered for data leakage is in-flight data, which means like data that doesn't really have an address space, which are basically buffers. So those buffers include load and store and line fill buffers. Now, here's an overview of how the RIDL attack works. Basically, the victim loads some secret data into the load and store buffer, then eventually it gets loaded into the line fill buffer. Subsequently, at the same time, an attacker can load the data into that same buffer, but in that process, speculatively during that process, during micro-optimizations, some data in the LFB gets leaked, and it actually resides inside of some of the cache lines. And this speculative data leak can be subsequently be indexed into the flush and store buffer for extraction. Now, here's a snippet of code that kind of showcases how this RIDL attack works. So first, the buffer gets flushed completely so that it can be prepared as a covert channel for the leak. Then after that, when you first execute the load, when you're loading in the new secret, the CPU has speculation, so it actually specularly loads information from the LFB. Now, eventually the CPU will catch on and actually load in the right value, but then traces of the LFB, like I said before, actually still exist in the corresponding cache line. Now, the rest of this code from line 12 through 20 actually sees which index actually was accessed the most recently, and then actually grabs that in the data entry that was, so it's like leaked. All right, now that we kind of showed a high-level example, let's talk more about line fill buffers. So a line fill buffer is an internal buffer which is used to monitor outstanding memory requests, and it's basically there for monitoring so that it can perform optimizations such as managing multiple in-flight stores and more of the like with monitoring like outstanding memory requests for optimization. Now the data in the LFBs can be speculatively loaded by the CPU as microoperations, like I said before, and these CPUs implement these speculation types really aggressively, and they don't have any regard to any virtual or physical memory address spaces. Now here are some experiments that the authors did to show that the line fill buffer can leak data secrets for them to exploit. So the first experiment here, we see 2 bars. So that's basically the LFB hit count versus number of attacks. So the left bar, the blue one, shows like how many hits the LFB got, and then the right one, how many data points got leaked. And as you can see, it's a 1-to-1 correspondence that all during SMT simultaneous multi-threading, all the data can get leaked. Now, when we don't perform SMT, which is the second plot on the right, we see that if it's in a different thread, it just reads a bunch of zeros. And if it's on the same thread, we can also see that most of the time the data can still get leaked. Now, in experiment B, we see that the frequency at which a secret A can be leaked, and through all the write through, write combine, flushing operations even, in write back and write through, we see that we hit more of the secrets in A than we do get noise. Now the conclusion from both of the experiments is that RIDL can leak from line fill buffers. Now let's move on to experiment C, which actually just shows this in a more complex sense, where we have multiple sequential secrets, which are written to sequential cache lines, and yeah, we can still leak the secrets is sort of as a kind of like a, not even, but like sort of in the same magnitude of distribution for the frequencies here. And lastly, this experiment right here, experiment D, basically shows like the ratio between 2 secrets. Like if you write one secret and then another, how much would that leakage be? Now doing this, we see that if we write to the secret A more often, it increases. And if we do more B, then then we will leak more B. The conclusion from both of these experiments is that we can use serialization, contention, and eviction to synchronize the attacker and the victim based on what secret we would like to leak. Now let's from the experiments that we discussed, let's see how we can exploit this using RIDL. So RIDL only requires the presence of in-flight secrets managed by the CPU. So in the top figure here, we see that we can do some sort of mask subrotate attack. Basically, we can use a mask to subtract and rotate, and we can selectively filter the data. Because like when we leak the data, it's not necessarily like all clean, like where it's all the data that we want. So we have to sort of selectively filter noise. So with this mask subrotate process, we can selectively filter out what data we want to recover or leak. And in the bottom figure here, we have that we repeatedly, and this is like an empirical result, we repeatedly invoke the password command from an unprivileged user, and eventually in that line fill buffer, the authors were able to recover the root entry in a matter of 24 hours, like 26 bytes in 24 hours. And there's a variety of other attacks other than cross-process and cross-VM, which are the examples here. There are kernel attacks. You can also leak arbitrary kernel memory. You can also do like page table disclosures, SGX attacks, and also JavaScript attacks. Now here's another type of side channel attacks that the authors also proposed. This is separate from RIDL, and this is based on the speculation of branches in data. So the first one we have is controlled speculation, which use direct branches. So in the code listing 2, we see that the attacker can control the X such that the conditional branch is always taken. Thus, the branch predictor unit would speculate on this code branch and like execute that if statement every time, and thus we will know the pattern and we can leak it to the cache-based covert channel. For indirect branches, in order for us to leak to the indirect branches, sometimes CPU have something called a branch table buffer, and we can leak that branch table buffer. We can poison it in order to do branch target injections. And there's also return branches that we can also leak data from, and we can do this by overflowing the return stack buffer and just speculatively execute codes in return. The problem, I guess the caveat or the downside of this is it only works with intra addresses. Another type of speculation attack is called data speculations, and in this we have something called exception deferral, and basically this is when the retirement unit is responsible for managing instructions that kind of retire in order from the CPU when it does out of order, but it retires the instructions in order, but executes the instructions out of order, basically. And the attacker can perform load and trigger executions during that sort of window before the retirement unit checks that, oh, okay, are you in order? But if you like leak before that window, the retirement unit wouldn't know. So here are some existing defenses. First of all, we want to inhibit the amount of time speculation triggers. And how Intel does this, which is the CPU brand that's targeted by this attack, is that they release new micro instructions such as IRBS, STIBP, IBPP to prevent poisoning of the branch predictor. Another common mitigation that we discussed before is KPTI, which basically isolates the OS and the user memory spaces, and it mitigates meltdown type of attacks. Now, with both of these defenses existing, when we try to use them against RIDL, they're rendered useless because these defenses, they don't protect you from the LFB, and the LFB, remember, is a buffer that doesn't really rely on valid or physical memory addresses. Yeah, and also these speculative triggers require these microcode patches, like when you want to inhibit speculative triggers, but however, they're not really readily deployed in much consumer products. And finally, KPTI requires a valid strict addressing requirement. And recall that LFBs don't really need that sort of addressing. So what are some new mitigations? When this paper was released, actually, the engineers at AMD reviewed this paper and they found that RIDL was actually an ineffective attack they're basically not affected by RIDL, which is good. So if you want to not get a CPU that is not affected by RIDL, get AMD. The second thing is you can also try to mitigate in software. So the first thing, as we saw in the empirical results from the LFB, is that when we disable simultaneous multi-threading, we see that not all the secrets get leaked. But however, this comes at the trade-off of reduced performance, reduced CPI, when you don't have simultaneous multi-threading. Another implementation is trying to flush the LFB, so that when we need to flush it before the attacker accesses it, so that data doesn't get leaked in the first place because the data is already gone. Finally, we can talk about spot mitigations, which is trying to like target RIDL mitigations one at a time. But the problem with this is that because of all the micro optimizations, just trying to search for these RIDL attacks can be really, really computationally complex. And yeah, finally, as a future work, we can implement similar exploits on other data sources, not just the LFB, but we can probably implement something similar with the reload buffer, for example, in order to exploit this attack. And here's a table here. I wanted to show you the latter three entries of this table, which are all AMD, are not affected by page fault, misaligned read, etc. So as a conclusion, we know that RIDL is a new class of speculative attacks that leak in-flight data. There are many usage scenarios, including a normal execution of the CPU, like during out of order, and in the browser, like JavaScript. And mitigation for these speculative attacks, these new speculative attacks, they are really ineffective against RIDL. And finally, the author suggested for future researchers to develop new architectures which have a blanket sort of solution to eliminate RIDL entirely. And here are the references, and thank you so much for listening to my presentation.